So, hello guys, we are going to look at a topic in chemistry called rate of chemical reactions. This particular topic can rather be called chemical kinetics. And yes, in the older days or in the older days of chemistry, we can relate the course with the topic with thermodynamics. In those days where before the industrial revolution, uh, most chemists are involved in, they are like, they are interested in, will this reaction take place? Not interested in how long will the reaction take place. How long will it take HCl to react with a particular component or a particular substance or compound? So was not the interest in those days. The interest was, will this reaction proceed or will it take place at all? So the rate of reaction is not a priority in those days. So, but later on, where industrial revolutions and we have competitions all around, we want a particular industry or a particular company that will quickly deliver its products on time and so on, chemical products to be precise. So then the need for us to speed up chemical reaction arises. Then we need to now study those things that governs chemical reaction. Then how can we increase the activity going on in chemical reactions and end up making it faster than it is? Firstly, we need to define what rate of chemical reaction is. I will take it in this form that we mix reactants, either 2 reactants, 3 reactants, or a single reactant in some cases of reaction like decomposition. Reactant is being converted to product. Those are the facts we need to understand when we are talking about rate of reaction. The fact remains that reactant is being converted to product. So we can define it in 2 ways. Is it the amount of product formed per unit time, or the amount of reactants converted to products per unit time? A particular reaction is proceed and 5 grams of each reactant is being converted to products in every 1 minute. You see the rate of reaction compared to a particular reaction whereby 5 grams is being converted to the product in 50 seconds, or let's say 25 seconds. So the rate is different from each other. So we are trying to study the speed of the reaction. So when you talk about rate of reaction, it is defined as the amount of reactants converted to products per unit time, or in the other way around, the amount of product formed per unit time. So the time you can decide to make use of minutes. You can decide to measure the rate of reaction with mass, which is being converted to products, with time in minutes, or you can decide to use your time in seconds and relate it with mass, or you use the concentration, that the concentration of reactant reducing with time, and your time can rather be, what I'm trying to say is that you don't have a specific value for time, like a specific unit of time. The time must always be in seconds. Generally, we know time must always be in seconds, but you can decide to work on the basis of minutes and mass, or you work on the basis of seconds and concentration, or mass and seconds, concentration and minutes, or sometimes hour if it's a type of reaction that is very slow. So now we can say the rate of chemical reaction in formula R is equals to change in concentration of reactants over time taken for the change. Over time taken for the change. So that's rate of reaction in that aspect, considering what? Concentration and time. So we can also consider mass. Rate of reaction can also be equals to change in mass of reactants over time taken for the change. So all these are simple calculations as far as rate of reaction is concerned. Let's take a look at a particular question. Example 1. Let's make use of a reaction like reaction between HCl and calcium transcarbonate. Okay, so let's say 50 grams of calcium transcarbonate CO3 is consumed in 2 minutes when reacted with HCl, that's hydrochloric acid or hydrogen chloride acid. Calculate the rate of reaction. Calculate the rate of reaction or the rate of chemical reaction. So to determine the rate of chemical reaction is very easy. So then I know that the rate of chemical reaction is equal to what? We are looking at mass with respect to time, and the time is a minute. So we can say change the condition of, there are some questions when we say change anyway. Rate of chemical reaction will be 50 over 2 anyway, so that means we have 50 and 25 grams per minute. Though when we say change, that is if we are given the first mass that started the reaction, then after some time we measure the time. After a little bit time, see, we measure the amount of reactants left, so we can determine the change in mass, final minus initial, by the time taken for that particular change. We divide that to get the rate of chemical reaction. So the rate of this reaction will be 50 all over 2, which is 25 grams per minute. So this particular reaction is measured with mass with respect to what? Time again. So the analysis might just come in this form, and we get things all right. So now let's proceed on rate of reaction as we discuss the rate curve. The rate curve. Rate curve is a graphical representation of all reactions. There are some reactions that are slow, but all reactions are fast at the beginning. No matter how slow a reaction is, it will be fast at the beginning. And no matter how fast a reaction is, at the beginning, it will be faster than the overall reaction. So as the endpoint is reaching gradually, we discover there is reduction in the speed of the reaction. So that is what the graph is trying to explain. So the graph is always fast, steeply fast at the beginning. So then gradually loses its potential as more of the reactants is being converted to products, or more of products is being formed. So then the graph is expressed in this form. So we have the graph, just like a straight line first, because it's very fast. Then on getting to this particular point, it begins to have a curve in this manner. So this happens to be the end point of reaction. Generally, this is the curve for all reaction. So the reaction is about going to endpoints here. So we have the products here. These are the reactants. So anyway, question might come in different way when you're about to study a graph, and though it's not rampant in Jamb and WAEC, but we have to at least understand the concept of the graph and know what the graph is talking about. So when you talk about the rate curve, this explains to us that the reaction is fast at the beginning, in this straight line you're seeing here, but on getting to a particular point, no matter how fast the reaction is, there will be reduction in speed. Though it might still be fast, but there will be reduction in speed of which it started with. So that's all reaction. So then the reaction curve always goes this way for every reaction. It always goes this way, because start with the high speed, then reduce gradually until you finally finish the whole reaction. That is what the rate curve is trying to explain. So this is the rate curve. And anyway, before a reaction could take place, you must have the minimum, the reactant particle must have the minimum energy required called the activation energy. So we can also take that into consideration. So we assume that before the reactants or the chemical reaction reaches this level, you must have gotten your activation energy as a reactant, then you will be able to convert into products at that particular point. So sometimes in the energy profile, this place is written as the activating complex. Though we are not trying to talk about exothermic or endothermic reaction, this is a red draw. We would have drawn it in an energy profile to show whether the reaction is exothermic or endothermic. But this is irrespective of the type of reaction, the rate curve always comes in this manner. So now let's go straight to the factors that influence rate of reaction. Factors that influence or that speed up the rate of reaction. I will shorten my reaction in this form. Now, when we talk about factors that influence, I said earlier that in the days of the earliest, or let's say the chemists, not the earliest, because earliest are the modern chemists, talking about the days where this particular aspect of chemistry is called thermodynamics. We are not interested in how fast the reaction is. All we are interested is will this reaction occur at all. So once we have established that, that's all. But now, industrial revolution has brought about various methods of doing things to make it faster and try to understand that okay, we need to study some factor as far as rate of reaction is being concerned. So before we can speed up a reaction, we must know some factors that guides it, that governs it. So then how to work on them to speed it up. So most of those factors, number one is temperature. We also have concentration. We also have pressure. We have surface area. We have catalysts. We have lights. Anyway, concentration and pressure almost have the same or close explanation, but just that this pressure has to do with gaseous substance and concentration. Even with gaseous substance, they have concentration, but we are going to explain it in such a way that it will be very, very easy to understand. Talking about temperature, we define temperature as the degree of hotness or coolness of a body. That's correct anyway. But let me cite an example with how this can help to increase the rate of reaction. When you talk about the temperature, according to collision theory, I must have explained that before I move to all these factors, but let's take it down there. Collision theory. Collision theory explains that before a reaction can take place, before a chemical reaction can take place, reactant particles must collide with a great force. When they collide, they get the minimum energy required, called the activation energy. Once they have this energy, they will be able to jump the energy barrier and turn into products. That was what collision theory explains. It explains once again that before a chemical reaction could take place, reactant particles must collide. They must collide greatly. Once they collide, it's more or less like, okay, I want to jump a fence and I decide to run in this way. I might not be able to jump over the fence, but if I increase my speed in this part, like an athlete trying to win a race, there is tendency that once I get to the fence, I will be able to jump. But talking about this kind of slow motion, I may not be able to achieve my aim in jumping the fence. So there must be a great collision. And out of all the collision, we have the effective collision and we have the ineffective collision. Effective collision is a collision that has not given the reactant particles activation energy to jump energy barrier and turn to a product. While the effective conditions are the ones that once you already have the activation energy, then you can overcome the barrier, the energy barrier, and turn into product. You must have. There is a question that normally comes out in one of the examination bodies that for a reactant to be turned into products, was option A says it must have activation, it must have energy equal to the activation energy. One says it must have energy less than activation energy. It must have energy greater than activation energy. The correct answer to this question is you must have energy greater than the activation energy. Because if you have energy less than the activation energy, definitely you will not be able to apply the energy barrier. But activation energy is called the minimum energy required. So at least you must meet up with the minimum energy required. So meaning having greater than activation energy gives you the tendency of forming the product. So that is what collision theory is trying to explain. So how can these factors now help us in speeding up the rate of reaction? Let's look at temperature. Heating a particular reaction, like two reactants are to combine, so then I have to heat the container, to heat it up so that it will speed it up from there out. So especially in this case, if the reaction can take place without heat, but trying to speed it up with heat. So what eventually happens when you heat, you are trying to increase the temperature of the system. So now, talking about the temperature. Once the temperature of the body increases, let us use human as an example. If you are in a cold weather, there is a kind of a relief that is always on us. We can relax and sit comfortably. But once there is heat, you are sweating all over your body you won't be at rest. Your system won't be at rest. You'll be like, you'll be like moving to where there is you can't just be you'll be restless at that particular moment. But if you are cool, you are in a particular cool condition, your energy in you, is will be a kind of a potential. But once there is heat, there is increase. Let's take it from boiling. The liquid molecules or particles were at least in slower motion compared to when you boil them. When you boil them, you are trying to increase their average kinetic energy. So once their kinetic energy increase, they will move with greater speed. So that greater speed makes them convert into vapor. So the same thing applies to all reaction. When you increase their speed, when you increase their temperature, the speed at which the reactant particle will move will be faster. And when they move with faster speed, they collide more frequently. They collide more frequently. So the frequent collision gives the high tendency that you're going to have effective ones. The frequent collision between reactant particles gives the tendency of having high effective collision. So, but in a case where you have smaller, the frequency of collision is not so much, then the tendency of having high, let's say, effective collision will be low. But when you increase the temperature, the average kinetic energy of the reactant has been increased. So they move with greater speed, so the collision will be rapid. And once collision is rapid, they will quickly attain their minimum energy, called the activation energy, and form the product. So that is why most reactions that is not known to be heated before are used to start applying heat on them to increase the rate of reaction. So increase in temperature now tends to increase the rate of reaction. That is for a particular reaction that is required to be heated. So now let's move to concentration. Concentration means the number of reactant particles present in a particular space. That is for temperature. I mentioned that of temperature. So let's look at concentration. talking about concentration, I have a smaller space here, and I have a space here. I have two reactant particles, three. Then I have in this same space, meaning the concentration here is low, and that of here is high. The concentration here, that means the amount of reactant particles, the particles present in solution or probably in a particular reaction is low here or is high here. Now, these particles are moving, they are in motion. The ones here are moving, the ones here are moving. There is tendency for us to have faster reaction here than here. Why? Because the distance between the particles are closer. So there is no how one of them will move without colliding with each other. So once there is collision and the collision is more frequent, they will definitely quickly get to the product or form the products. Why this? There can be movement without collision because there is enough space. Okay, just like we have two keys to move in this particular room, except if one of them wants to cause trouble. That is the only time you have to go and push the other one. Yes, but there is enough space, so they can both move without colliding, without touching each other at all, except if there is a troublemaker among them. But in the case whereby you put about 100 people in this room, there is no how they will move without touching each other. So definitely there will be collision in such reactions. So that is how concentration increases the rate of chemical reaction. So when we have high concentration, it helps to speed up the rate of chemical reactions. Now we can move straight to pressure. Pressure is more or less similar to concentration. Pressure is more or less similar to concentration. Reason being that when you talk about pressure, pressure has to do with decrease in volume across according to Boyle's law. The volume of a given mass is inversely proportional to pressure, meaning that once the pressure increases, meaning that the volume has decreased. Once the volume increases, the pressure has decreased. So if I have a gas, this is for pressure. If I have a container, another container that contains the reactant particles, so I have gases, the gaseous reactant particles. The volume of the gas, gas occupies no space, it occupies any volume. So and then in this particular case, there is enough space for the gas to occupy. And despite that fact, there is still gap between the two reactants, the gaseous reactants. Though there will be collision because gas are continually in motion and they will definitely collide. But to increase the collision, if you increase the pressure on this particular reaction, there will be what? Increase in rate of chemical reaction. How? Because exerting pressure, reducing the volume will increase the pressure automatically. So if I apply a piston to increase the pressure and reduce the volume, meaning I insert the piston into this, then press it down. The gases, there is no space for them to escape anyway. Meaning all the gas will be packed to the downside, and the space between them will reduce. Don't forget, you have increased the pressure that way because once you push gases together, there is tendency that they want to go away from that kind of position. Like gases that are normally moving in occupies all space, and you try to trap them into smaller space, so they will tend to apply more force in order to lose that to escape. So that means the pressure has been increased, but yet increasing the pressure has reduced the volume, and the gap between each gaseous reactant has been reduced. So there will be frequent collision. It's more or less like a concentration explanation, because in concentration we're talking about gap between them because there is not enough reactant particles, the reaction is slower. So talking about this also, That is why I said there is a similarity in pressure and concentration. So increase in pressure for gaseous reactant also increase the rate of chemical reaction. So now let's move to surface area. I once asked someone that talking about surface area, how does it affect the rate of chemical reaction? Um, we have talked about, okay, those that take pap or probably a beverage that involves you dissolving sugar and so on. If I make use of a cube sugar, I will have to wait for it to dissolve in mix. If I use of a powdered one and I add this directly, I mix, I take this straight away. Or probably in this direction, I have a particular salt that is in lump form, is in lump form, meaning is a little bit bigger particles. Then I have another one in powder form. I'm meant to dissolve both in water. The one with powder form will evenly be distributed in the water and dissolve faster than the one in lumps. Because of the surface area, there is enough area for the reaction to take place in terms of dissolving the powdered one. But the lump, there is not enough area, so it has to be gradually. So one will be faster than the other. So if I want to make the one with the lump faster, then I'll have to grind it or pulverize it into powder form. So that is how surface area increase the rate of. So most of the parameters increase in temperature, concentration, pressure for gaseous reactant, and surface area for solid reactant always increase the rate of chemical reaction. Then we also have catalysts. Definitely we know catalysts are a substance that speed up the rate of chemical reaction, they alter the rate of chemical reaction. Anyway, we are much more familiar with that. How does catalyst affect the rate of reaction? How? Because when we add catalyst to reaction, they remain the same. Their molecular formula and everything about them chemically remain the same. But they help to speed up the chemical reaction. How? Catalysts help to speed up the chemical reaction by reducing the activation energy. Let's assume I have a particular reaction. Let me use an energy profile as an example. This is the energy barrier. That must be overcome before that particular reaction takes place with product, and this is from reactant. What catalyst does is that catalyst help to reduce the energy the reactant particle need. Like, okay, for a normal reaction without catalyst, each reactant particle must have about 50 joules of energy. But once catalyst is introduced, catalyst might reduce the energy required by the reactant to 35. So something you are required to make use to have 50 before you can achieve it, and you're having 35 before you can achieve it. So then that means there is a speed up in the chemical reaction. Then catalyst helps to reduce the rate of chemical reaction in that form. So then we have light also. So adding of catalyst to the chemical reaction helps to increase the rate. Then we have light. How does light help to increase the rate of chemical reaction? So most of photochemical reactions are of this. When we talk about photochemical reactions, we are talking about reactions that involves light, that take place in the presence of light. So example of such is reaction between methane, the alkane CH4 plus chlorine to produce probably CH2Cl2 plus H2 gas. So this particular reaction must take place in the presence of light to make it faster. But in the absence of light, to be very, 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 very slow. So this type of reaction are called photochemical reactions. So without light, they may not take place faster. So this is where we're going to stop today. Thanks for watching, and please subscribe to our YouTube channel if you are new. Please, if you are old, thanks for coming back again. Thank you. let's look at order of reaction. So when we talk about order of reaction, so when we finish with order of reaction, we take this question as a means of like rounding up this particular topic. So what is order of reaction? Firstly, I will need to explain some certain things. If I have reactant A plus reactant B giving us reactant C, or probably reactant C plus D. What do I mean by order of reaction? The concentration of each reactant and product will be given this way. This bracket, square bracket, means concentration in chemistry. It means concentration. Once this square bracket is being used in chemistry, it means concentration. So if I write this, it means concentration of A. That is what it means. So now, what is rate of reaction having to do with order of reaction? If I rewrite this reaction in this form, reactant A, the number of moles of reactant A, let's represent that with M, and the number of moles of reactant B, let that be N, equals products, let's say P, C, plus Q, D. Anyway, the order of reaction is defined as the power to which the concentration of reactants must be raised to give appropriate rate of a chemical reaction. I repeat again. The order of this particular reaction is defined as the concentration to which the power of the reactants must be raised to give the appropriate rate of reaction. That is what order of reaction is talking about. So what do I mean by the power to which the concentration must be raised? So the power to which the concentration must be raised is talking about the number of moles of the reactant in the equation. So now let's go along by calculating the order of this. Order of A is equals to concentration of A raised to power n. Order of B is equals to concentration of B raised to power n. That is what order of reaction means. So we have orders. When we have first orders, we have second order and third order reactions. What do I mean by that? The first order is a type of reaction in which the overall order of the reaction is 1. I will cite an example. I don't want to drop this question. Let's take a look at this reaction. I have a reactant A plus reactant B goes to C. The number of moles here is 1, 1. So if we are to consider only one of the reaction, it has only one order. So the order of the reaction, we have the order of A, which is raised to power 1, dot the order of B, which is raised to power 1. So overall order will be equal to the order of A plus the order of B, which is 2. It shows that reactants with reaction with 2 reactants, of which the number of moles of each reactant is 1, 1. Such a reaction is a second order reaction. Once the whole order of the reaction, once the overall order of the reaction is 2, then is a second order reaction. Let's take a look at this reaction A. Reactant A that forms product C. So this is a first order reaction. Why? Because the order of A raised to power 1, the overall order of this reaction is 1. Don't forget, we are not concerned about the products. So now I can also look at a kind of reaction like 2A goes into the formation of C. So the order of this particular reaction is 2. So this is the second order of reaction. So order is what? Order is 2. That's second order reaction. So we also have zeroth order. Zeroth order. Zeroth order in such a way that the concentration is raised to the power of 0. So this is zeroth order of A. So the order of reaction has to do with the power to which the concentration of reactants must be raised to give appropriate rate of reaction. So let's look at a question that says, okay, we should determine the order of this particular reaction. A plus 2B is equal to C plus D. The concentration of A, and don't forget, there is a law that says the rate of reaction is proportional to the overall order of the reaction. So how do we get the overall order? That's concentration of A raised to power 1 dot concentration of B raised to power 2. So anyway, this is a law. But talking about the order of reaction, we are only specifying order of reaction. So the order of this particular reaction is what? Is 3. So this reaction is called order because by adding power function of A with B, it gives us 3. Another question. So we can have a deep understanding about order of reaction. A plus B plus C all equals D. A reaction. The order of this reaction, the overall order, will equals to 3. So this particular reaction is also a third order because the number of moles of each reactant is 1. So the concentration will be raised to the power of what? The number of moles. So which is 1. Adding it together will still give us 3. So this type of reaction is still third order. So and many more, the form of which the reaction comes, just add the number of moles of each reactant together to give you the order of the reaction. And it is defined, the order of reaction is the power to which concentration of reactants will be raised. So that is why in all my writing, I always prefer to write it this way. So this shows that it is third order reaction. So that is all about order of reaction. So let's quickly look at this particular question here about the factors affecting the rate of chemical reaction, and a question, a frame of question that we at least brush us off a little bit. In an experiment, excess 0.5 mole per dm³ HCl was added to 10 grams of granulated zinc. So we are talking about a reaction between zinc solid plus HCl aqueous to produce ZnCl2 plus H2. So meaning we're going to balance the equations with this. So we're talking about this particular reaction. Gas solid of aqueous. So now, talking about this particular reaction, 0.5 mole per dm³ of this, the concentration of 0.5 mole per dm³ of this is added with 10 grams of this zinc in the beaker. Other conditions remain constant. So now we said state how the reaction will be affected in each case if the experiment was repeated using the following. So now, how will the reaction be affected if probably 1.0 mole per dm³ of HCl is used instead of 0.5 moles? The solution to this question is the reaction will be faster. The rate of chemical reaction will be faster. Why? Because there is now increase in concentration from 0.50 to 1.0 of that of HCl. So in this particular question, I said making use of 1.0 mole per dm³ of HCl will increase the rate of reaction. Using 1.0 mole per dm³ of HCl will increase the rate of reaction. Now, making use of 8.0 gram of granulated zinc. So now, meaning that the mass of zinc used now reduced. So definitely, since the mass is reduced, the concentration also was reduced. Then the rate of chemical reaction is lowered. So rate of chemical reaction will be faster than the normal reaction that was done here. And in the first case of number one, rate of chemical reaction will be faster than the initial one explained here in this experiment. If it were to be this used, and if it were to be 8.0 gram of granulated zinc used, the rate of chemical reaction will be reduced. It will definitely be reduced. Now, moving to 10 gram of zinc dust. Don't forget, in the question, it was stated that 10 gram of granulated zinc was used. There is a difference between granulated zinc and zinc dust. Their surface area is different. So surface area comes in. So meaning zinc dust, 10 grams, the same mass of zinc dust, or the same mass of granulated zinc was used here, and the same mass of zinc dust was used. So this shows that the reaction will be faster here due to the surface area of zinc that is available, because zinc dust has more surface area compared to what? Granulated zinc. So this part, using 10 gram of zinc dust will increase the rate of chemical reaction. Now, going to a reaction vessel dipped in crushed ice. When you dip the reaction vessel into crushed ice, you have lowered the temperature. You have reduced the temperature. So then what will happen to that of reaction? That kind of reaction will be lowered in rates. And the rate of reaction will be reduced because increase in concentration has been confirmed to increase the rate of chemical reaction. So putting the reaction vessel in the crush of ice will lower the temperature, thereby reducing the rate of chemical reaction. So let's go to the last question that says a higher volume of 0.5 mol per dm cube HCl is used. When you use higher volume of this same concentration, what will happen to the rate of reaction? When you use higher volume of it, the reaction still remains slow because the number of moles of HCl in solution is still 0.5. Using higher volume has also what? Increased the space. It has increased the space for reactant particles, so then there won't be frequent collision, unlike using smaller volume of this concentration. Using smaller volume of this concentration will even be faster than using higher volume of this concentration. So these are the form of question that it might be in form of objective or probably a theoretical question. So the idea are meant to be used within each interchangeably in solving question for rate of chemical reactions. So thanks for watching. Please subscribe to our YouTube channel, it's free. If you are new here, please subscribe. If you are old, thanks for coming back again.